At the end of 2018, Walkers launched their own recycling scheme for crisp packets after more than 300,000 people signed an online petition demanding that they change to a fully recyclable material for their packaging. Crisp packets are made from plastic coated with a thin layer of metal. The metal layer is essential to prolong the shelf life of the food by providing a barrier to oxygen and water, but it makes the package very difficult to recycle. Aiming to tackle this problem is Dermot O'Hare and his team at the University of Oxford, who have developed a new coating using nanotechnology, which, they say, could produce fully recyclable crisp packets and other plastic food packaging. I'm Heather Jameson, and I spoke to Dermot to learn more.
So a crisp packet, when you open it, you see a shiny inside. So that is actually aluminium, which has been deposited on the backside of the plastic film and then coated with a clear layer. So the aluminium isn't actually in contact with the food, but you see it through a clear layer. Or you open a coffee bag or a sachet of some dry food or a nut bar or something like that. Metallized film is used very, very widely globally as a packaging technology. It's used to prevent oxygen and water vapor diffusing into products inside the packaging. And it creates a physical barrier for these molecules. And so we want to create a new barrier. So we've come up with a technology where we create tiny little platelets composed of magnesium and aluminium hydroxides. These are nanometer thick materials that we have fabricated in our lab in Oxford. And the idea is to lay these tiny little platelets on the surface of the plastic film. And they all interlock beautifully, just like a deck of cards been spread on the table. And they create a very tortuous pathway for these molecules to diffuse, because the molecules can't go through our little platelets, they have to go around them. And so by the process of winding your way around all these little platelets lined up on the film, they basically give up and they end up not diffusing through the layer.
And why is this new coating more easily recyclable?
I think you've got to look at a few aspects to that. So fundamentally, you cannot very easily separate the aluminium from the plastic when you take a metallized film through reprocessing. That's an issue. And also there's quite a lot of this metal on the layer when you kind of work it out. So it's actually quite a large component in terms of the mass, whereas our system uses tiny amounts, milligrams of the material in any square meter of the plastic. So we use a lot less, and it actually just dissolved away when it went through a reprocessing technology. So the aluminium you have to physically separate, whereas our materials will just melt away into the plastic. And actually it might even improve the plastic.
In your new material, is that as good at acting as a barrier as the metal?
Yeah, from what we have tested and the sort of benchmark metallized films we have bought and tested, we're about 40 times better, like for like, using the same plastic.
Is it any more energy intensive to make this new coating and put it onto the crisp packets?
Actually, it's really energy good in terms of carbon footprint. So let's just go back to how you would make a metallized film. Metallized film is made by vaporizing aluminium metal onto a roller of plastic as it runs across a furnace. So aluminium's boiling point's over 2,000 degrees. You can imagine the energy it takes to coat millions and millions of meters and how much aluminium is used in that. And we make our coating at room temperature.
You've talked about this coating being used for food packaging. Are there any other applications that this could be used for?
There are extremely high requirements in some sectors of aerospace, in some battery technology, and in semiconductor technology for oxygen barrier and moisture barrier. There is another technology which is super expensive to do, which is what they currently use. So it's so good, this film. We've got such great oxygen barrier performance. We actually may be able to attack that problem.
That was me, Heather Jameson, speaking with Dermot O'Hare from Oxford University, and that work was published in the journal Nature Communications.